Hi, in a previous mailbag, which I'm going to link in down below, I opened these PCBs from JLCPCB and said that they are for an RF splitter or RF divider. I'll probably use both terms. And in fact, this divider can also combine two signals into one as well. So as well as being a divider, it's an RF combiner. I've said two signals, it could be more, but for the sake of the video, let's just deal with two, because otherwise it's going to get very complicated. Now this is a Y splitter, that's its name, and you'll see why in a moment, and I'm going to assemble it and give it a quick test. Now the best insertion loss that a splitter can have is 3 dB. So that's because each output has half of the power that was inputted. So we input some power, we split it in half, and it goes to the two outputs. Now that's 3 dB loss. Now the Y divider has a 6 dB insertion loss, which seems quite high. But it's a bit of a trade-off because the Y divider is really wide bandwidth. In fact, it goes all the way down to DC and can go up into 20-50 gigahertz in some instances. Not with a homemade one, but if you buy one from Tektronix or Keysight, you can certainly get 50-60 gigahertz bandwidth. If we want to have smaller losses, then we have to compromise on the bandwidth, and we're going to make those using inductors, capacitors, transformers, that type of thing. They're not going to do DC, and yeah, they'll do some sort of bandwidth, but as we want the bandwidth to increase, the complexity of the splitter will increase tenfold. So I just needed a simple divider that would be general purpose. I wanted to go from a few kilohertz up to a few hundred megahertz, and that's why I've chosen this design. Now, I haven't gone mad with this design. I haven't done huge amounts of RF simulation or anything like that. I've just made a board to put it on. It's an impedance control board, but other than that, there's nothing particularly special about it. And I'll talk about some of those design points as we go through. Now, I've seen a few people making their own dividers, often just sticking a few resistors in a box, and I've wondered about how good they are performance-wise, but few people have actually bothered with putting anything up about performance checks. Now if we look at this board, we can see that there are going to be some problems. This is supposed to be a purely resistive circuit with 50 ohms impedance, but it has things like quite a lot of pads for resistors and that sort of stuff, and those have all got capacitance, and of course the leads have got inductance and so on. So this is not going to perform perfectly. And I think it will be interesting to see various different designs. So I'm going to try one with where all the resistors are combined into a single 805 package. That will be quite an interesting thing. I'm going to try bunging some through-hole resistors in a box, and I'm also going to try a commercial one, and I'll also try and do some sort of surface mount but without a proper PCB, just to compare how they all stack up. Now I can't afford a Keysight or a Tektronix divider, so I'm just going to use the data sheets when I come to do the performance testing and just get a baseline from them to compare my own homemade ones. Okay, so before we build up the various types of splitters, let's just have a quick look at the circuit diagrams and look at things like impedance matching and things like that we need to think about, and also just think about what we're going to measure as well. Already got some knowledge of RF dividers, particularly the Y-type divider and Delta-type divider, and you understand about impedance matching and that sort of stuff, then please skip ahead. I'll put a link in the chapters so you can move ahead and miss out this section. However, if you're just getting started and you're not familiar with RF, then this is a good idea to take a look at this bit, I think. So let's think about splitters and dividers. We've got some power coming in, and we want to split it into two or more parts and have that used by several consumers of that power. So our power is going to just flow through and split, hopefully, between these two outputs. Now there's a few things we're interested in. First of all, we would like the power to be split evenly. So this has to be very symmetrical in its design. What else do we want? Well, this is an RF circuit. So in an RF circuit, all of the inputs and outputs are supposed to have 50 ohm impedance, and to transfer power well, we need all of those impedances to be matched, and all the cables need to be 50 ohm impedance, and all of the things like splitters and dividers also need 50 ohm impedance. Now if we just have basically a T-junction, then do we get 50 ohms? And the answer is no, we do not. what happens if it's not 50 ohms? Well, the answer is that some of the power bounces back and goes out of the input. So this is what we call a reflection. So we would like to keep our reflections fairly low. We'd like our, because that's power that isn't getting to the output basically. So in an ideal world, we would input our power, it would split between the two outputs and nothing would ever get reflected back. What else do we want? Well, I've already said we want them to be evenly split. Is there anything else? Yes, we would like them to be phase matched. So we don't want any shift in phase between the two different outputs. Ideally, we don't want a shift in phase between the input and the output either, but that's actually not really possible because there is physical length in these dividers. If we're building them directly into a more complex circuit, then we can make the divider really, really tiny, and I'm talking sort of 0402 size. But in practice, this is a general purpose divider with connectors and things like that. It has physical size, so it will have phase shift. A resistive divider is certainly the easiest way of achieving this. Now, what happens though if we do try and just use this divider here? So when we plug in our devices that are going to consume the power that we're dividing, they each have 50 ohms impedance. So they look like a 50 ohm resistor going down to ground as far as the circuit is concerned. So now, if we've only got one circuit, then we'll put a 50 ohm terminator on the other one. So what is this? What is the impedance of this circuit just here? Well, ignoring any parasitic capacitance and inductance and stuff like that, this is the same as two 50 ohm resistors in parallel. Now, two 50 ohm resistors in parallel works out at 25 ohms because it's half. It's an easy calculation. And therefore, this circuit doesn't have 50 ohm impedance, it has 25 ohms impedance. So the matching between the 50 ohms input source and 25 ohm consuming it. So that's absolutely no use whatsoever. We're going to get massive reflections back, we're going to have lack of power transfer, and we're going to lose 10 dB or more in terms of the actual transfer power. So that's useless. Here is the Y divider circuit. Its power goes in and we have 16.7 ohm resistors in each leg. So this is still like a T junction or Y junction, I suppose, except it's got 16.7 ohms in it. And we can see that instead of minus 3 dB, we're now losing minus 6 dB, and that's simply because we've got these resistors. But we need the resistors. We've seen this diagram, let's move on and have a look at it with the resistors in place. So here's our Y splitter, and we've got our 16.7 ohms, and here are our 50 ohms, just like they were before. So we can see now, if we think about trying to solve out what do we see from this end here, I want to see 50 ohms looking into this circuit. So I've got 50 ohms in series with 16.7, so that is 66.7. I'm going to try and write here. This is going to be really clumsy. I'll do my best. So I've got 66.7 here, and I've got 66.7 here. Now those two in parallel come out as what? 33.35. So still not 50 ohms, but we've still got this 16.7 just here in series. So we add that on and we end up with 50.05, which is 0.1%. Now, given that these are going to be probably 1% or 0.5% tolerance resistors, then ending within 0.1% is absolutely fine. If you want to be tighter, then you could get some 16.666 ohm resistors at a 0.1% tolerance and enjoy seeing your bank balance go down, really. So there we go, that's how we see 50 ohms going in, and because this is entirely symmetrical, any of the three connections could be the input and any of the two could be the output. There's also another variation on here which is called the delta splitter or divider. So it's similar sort of layout, but in this case you can see we've got 50 ohm resistors in the delta. Although actually if you buy a 50 ohm resistor, they're quite pricey. Most people buy a 51 or 49.9 ohm. Very similar sort of calculation for this one. It's doing exactly the same job. It's impedance matching. So our power comes in and splits as before, and we've got our 50 ohm resistors on the end just as we did before. So how do we solve this resistance network? Well, the key is actually a sort of easy way really is to think about this. We've got power coming in here and splitting out, and if we think about this just here, this point here and this point here, so let's draw them on points, that point there and that point there, the voltage at those 2 points must be identical because this is completely symmetrical. So if that's identical, then there is 0 amps. So there's no current flowing through this resistor at all. Well, that then is the same as we can either consider that to be a short circuit. Forget about the resistor, we'll just put a short circuit in there because that's how you get the same voltage. If you put a short circuit in there, then these two, so this one and this one, are now in parallel. So that's 25 ohms. And this one and this one are also in parallel, so that's another 25 ohms. And those two 25 ohms are in series, that makes 50 ohms. If, however, we consider this to be open circuit, so we just say, we'll just ignore the resistor, since there's no current flowing through it, it doesn't actually matter, then what we get is 50 ohms over here, plus another 50 ohms over here. That makes 100 ohms, and there's 100 ohms in the bottom leg as well. And those 200 ohms are in parallel, which makes 50 ohms again. So that's how we can achieve our impedance matching, either using a delta splitter or using a Y splitter. So theoretically, this is an entirely resistive circuit and therefore has unlimited bandwidth. In practice, of course, these lumped components, the resistors themselves, they will have capacitance and they will have inductance, even though they're quite small. It, of course, is easier to keep that minimized if we use surface mounts, and particular types of surface mounts will have less capacitance than others. So our problem here is our parasitic capacitance, parasitic inductance, and there'll also be that in the connectors and things like that. Now, I had a problem when I was getting my 16.7 ohm resistors in that all of my normal suppliers were out of stock. And in fact, most of them are still out of stock. I have noticed that Mouser have got a few in now, so I have actually ordered them. But in the meantime, I've actually done this in my little circuit, which is I've put two resistors in series to make the 16.7, and they are an 8.45 and an 8.25. So I've done that to make my 16.7, which is kind of fine. The problem is now I've got quite a lot of pads on the board, so that's quite a lot more parasitic capacitance in particular that's going to appear on the board, twice as much as if I'd just got the original 16.7. Power wise, however, it's quite useful because the power is basically split between two resistors now, which means in actual fact instead of creating a quarter watt divider, I'll be creating a half watt divider, which is, you know, kind of good. Okay, let's go and have a look at the different implementations of this then. So here are the 5 circuits I'm going to test. At the top right, we've got the Y splitter that we've described and we started the video with. To the left of that is another Y splitter, but in this case I've used a custom made single resistor array, which is mounted on the back of this, and I'll show you that in a second, to try and reduce the parasitic inductance and capacitance further. On the left hand side we have got one which I've bodged together just using 0805 resistors on a bit of perf board and a bit of copper behind it to link up the grounds. Bottom middle we've got the commercially bought one, which is just a Y configuration, and you can easily see the Y on the surface, and 3 resistors, and this is a planar design as opposed to mine which uses a multi-layer design. And bottom right finally we've got a metal box containing 3 resistors that are just soldered in a delta configuration onto 3 connectors. These are through hole resistors, so you know, big bulky things. Now I'm not going to show you all the design and assembling them and stuff like that, it's just boring really. What I will say is that my boards are a 4-layer design using one of the impedance controlled stack-ups from JLCPCB, and they provide all the track widths and the layer information and that sort of stuff. So I'm showing on the screen at the moment the one that's using the little integrated 3 resistors in one package. It's actually got a connector on either side of the package, like an 805 resistor, and 3 additional pads underneath. This means it's a bugger to fit because it requires placement like it's a 201 part. These pins are absolutely tiny. Now, had I known this, I would have gone for, they do a couple of bigger parts of similar specification, and they would have been slightly easier to fit, but not much. I ended up actually having to apply the paste onto the part to try and keep everything clean, because there is a piece of metal, there's a metal connector right on the bottom of it, and there's a clearance of 0.2 millimeters is how much you've got between the pads. So yeah, really hard to fit. But anyway, I got there eventually. Let's see how it works out. So here's our first trace, and this is from the commercial one. Now, one division down from the top is 0 dB, and the red line at the bottom is the VSWR. So if we take a quick look at this, we can see that we have a blue line, which is the insertion loss. So that should be 6 dB, but it's measuring 10.9 dB down. We've got a purple line, which is the S11, which is the amount of reflection or the return loss. And we've got a red line, which is the VSWR. So the VSWR wants to be about 1.2 or lower, and in this case it's sitting at 2. So 0 SWR is 2 divisions up from the bottom, and then it's 1 SWR per division. So what about our return loss then? That's minus 9.19 dB, and ideally we want to be looking at better than 20. 20 would be really good, and anything less than 20, so minus 30 for example, would be great. Minus 9 is not very good at all. Similar with VSWR, we want about 1.2 or 1.15 or anything lower than that. 2.06 is not acceptable. And if you look at the Smith chart, we can kind of see there's a messy red line running down, and it doesn't even hit the 50 ohm center point on the Smith chart. So that's pretty awful. In fact, minus 10 dB is very surprising. So here it is from eBay, complete with incorrect size resistors fitted to it. So someone clearly has not got a clue how this works and decided that fitting 51 ohm resistors is fine. If this were a delta configuration, then that would be absolutely okay, but this isn't. This is a Y configuration and wrong size resistors. So at some point I will buy some 16.7 or 16.66 ohm resistors and stick them on it to turn it back into a working device. Okay, so next up I will plug in my homemade Y configuration with the 6 separate resistors on it, and a 50 ohm terminator of course on the extra. Let's just hit the run on that. Okay, and this is considerably different. So I've got this set to 46 megahertz at the moment, and we can see that we've got 6.02 dB forward insertion loss. That's the top blue line, and that's pretty flat. It's obviously decreasing as we go along. Our return loss, which is the purple line underneath, minus 35.2, which is outstanding. So that's very, very good indeed. And we can see our VSWR is 1.04, which again is also outstanding. And across on the right hand side, we've got 49.75 ohms of impedance. So really well matched overall. In the center of the Smith chart, we can kind of see that we start off exactly on the 50 ohm point, and then we're dropping down, and yeah, we're getting capacitive. All the bottom part here is all capacitance, which is affecting the inductance slightly. So our inductance is reducing due to capacitance. So, you know, not a bad match though generally. Let's have a look at a different frequency. So this is our worst in terms of return losses. So the purple is pretty much at its top. We've got a VSWR of 1.46, which is a bit high, but just about acceptable. Minus 14.61 dB return loss, or reflection if you prefer. and that's at 749 megahertz. So, you know, what can we say about this? It's sort of acceptable across most of the 1.3 gigahertz that we've got here, but it's not great. And certainly, you know, you probably only want to use this up to 400 or 500 megahertz, I suspect. But overall, did we manage to get the 200, 300 megahertz bandwidth out of it that I was intending to? Absolutely we did. And we got exceptional performance all the way up to 200 or 300 megahertz. And it's pretty good as well as we sort of start heading up into the very higher frequencies. But anyway, there we go. So yeah, that capacitance that we talked about, that definitely does affect stuff. So if we look there, 308 megahertz, that's looking pretty decent. 1.22 VSWR and 20 dB return is an excellent result. Okay, we repeat the experiment, but this time we're going to use the very smallest board that I use. This is the one with the resistor array on it, and it's physically smallest and the one I predicted to be best. So let's have a look at the result. This is obviously connected up identically to the previous ones. So first impressions of this is outstanding. Let's take a quick look at the center blob to begin with. So this is the Smith chart, and instead of being spread all over the place, that is nice and tightly defined now. If we look at the insertion loss in line 1, so I've got 312 megahertz here, and you know, it's pretty flat. I mean, we're just running along the 6 dB down line. It's almost identical to the theoretical output. Return loss at this point, minus 48.66 dB. That's absolutely stunning. SWR is 1.01. So, you know, yeah, this is certainly at the low frequencies here, 42 megahertz is unbelievably good. The matching is 49.76 ohms. You know, so yeah, there's nothing to say bad about this. This is absolutely outstanding performance at the low frequencies, and we can see we can get quite a way across the graph before we even begin to pick up any bad news. So the VSWR is pretty flat right across the entire width. It's, you know, there's no appreciable figure on it right to the right hand side, 1.3 gigahertz. The return loss is, you know, fantastic all the way across. And in terms of S11, the actual purple line in the middle, look at this. I mean, we're up to 500 megahertz here. We're still minus 36 or so, 600 megahertz, minus 37. Yeah, we barely even touch the 20 dB return loss, which is kind of, 20 dB would be good news, it's excellent. Anything lower than that is outstanding, really. So we start at the left hand side. Certainly the first gigahertz is outstanding, and then we just move to excellent for the last 300 megahertz. Fantastic. And as I said, there's not too much capacitance there. The big difference between this and the other one is just that capacitance that we can see from the Smith chart in the middle. So in fact, I'm going to put this onto a wider range vector network analyzer in a few minutes. It won't be quite as clear on the screen, but it will enable us to test it up to 3 gigahertz, because this is absolutely fine all the way up to 1.3. So just for a bit of fun, I've superimposed on this the previous trace from the other one that I made, which was surface mount resistors, but they were discrete and spread out a bit, so greater capacitance. And yeah, that's the difference just on that one component, really. And of course a slightly smaller board, but it's mainly about that capacitance on the pads, as we discussed and predicted. So I'm just saving that very good trace into memory so we can use it again later, and now I'm going to test this little bodge together one on a bit of perf board. Oh, this looks bad. So, okay, so first impressions are obviously that we've got a huge purple line springing up to the top, and we've got a huge red line in the middle of the Smith chart, which is all inductance. So we've got rid of our capacitance problem, which isn't surprising because this is just some 805 resistors soldered one directly onto the next and onto the pins. There is no PCB for the capacitance to be there. Yeah, the forward insertion loss is sort of alright, but the return loss, of course, is a disaster. So there's 137 megahertz. Yeah, and yeah, essentially, Yeah, we just got ridiculous amounts of reflection at the higher frequency. So I don't know what this really works up to. I mean, if we say 15 dB, they're about 395 megahertz. Yeah, it's sort of vaguely acceptable up to that point. The VSWR there is 1.5, which is why I chose to stop there. But yeah, okay. So you could use it up to that sort of frequency, but in truth, you probably only want to use it to about half of that, maybe about 200 megahertz, something in that region. But it's interesting, I think, because it does illustrate the fact that we've shifted away from our capacitive problem and gone to an inductive problem. But you know, the end result is the same. Its return loss is dreadful. Now, having seen how bad the Bodge together one using surface mount was, I'm a little bit nervous about testing this one in the can that's using through-hole resistors, but we'll get on and do it anyway. So if you remember, this one's a delta configuration, through-hole resistors, and if I ever get this 50 ohm terminator on it, then we can have a look and see how that stacks up against the surface mount. This is the one that I predicted to be worse. And this looks really, really dreadful. I've actually got the marker set at 139 megahertz, and at that point it is actually acceptable. So yeah, and you know, at a few megahertz it's fine. 40 megahertz there, you know, 6 dB forward loss, minus 25 dB return loss, VSWR of 1.13, so that's absolutely fine, and 50.09 ohm impedance, so not a problem. So we can certainly get up to 100 megahertz or something in that region. But beyond that, it's absolutely awful. If we look at the Smith chart, we can see that that inductance is completely dominating. As soon as we get off DC, really, it just turns into an inductive nightmare. So there we go, 139 megahertz is our sort of acceptable cutoff, but I wouldn't really want to go that far, probably only as far as 60 or 70 megahertz. And that isn't really surprising. It is big, lumpy, through-hole components, of course. So I said we'd look at the data sheets for some major manufacturers. This is a Textronics device, and the top right-hand graph is the return loss, which is the one we're really interested in. And as we can see, we vary between about 35, minus 35 to minus 15 dB across its bandwidth. Now this is 25 gigahertz bandwidth, but even so, that's kind of where I'm taking my sort of starting line from, and we can see that they do actually drop a bit in terms of the insertion loss as well, dropping down from 6 to about minus 8 dB. Most of the manufacturers unfortunately do not show the S11 chart, but they do all list VSWR, and so this is a top class device, and the SMA version, for example, has a VSWR of 1.2. So my best device is generally beating that or equaling that for most of its bandwidth. If we look at the Keysight, so here they quote both dB and VSWR. So if we look at, for example, the 1163B, then DC to 10 gigahertz is a 20 dB return loss, which is very similar to what I've been achieving, and that's a VSWR of 1.22. It worsens a bit as we go up towards the top end of the frequency. But anyway, I thought I'd just do that just as a bit of a cross-reference and a sanity check against my readings. Okay, so doing this on the computer screen with that low-cost vector network analyzer was quite useful, but I figured I would plug it into something a little bit more beefy. This will enable us to actually look at the best of those devices all the way up to 3 gigahertz. So there's no point in looking at most of them. So this device, for example, was pretty good, you know, to a few hundred megahertz, not a problem at all, and perfectly usable for what I actually want to use it for in this instance. But the one using the little single tiny, very annoying resistors all in one package certainly outperformed it all the way up to 1.3 gigahertz. So it's worth plugging into something else and just seeing how well that performance continues all the way up to 3 gigahertz. I would like to test it beyond 3 gigahertz, but unfortunately, this is the highest frequency vector network analyzer I've got. And here is our return loss, our S11 parameter. And ideally we'd like that to stay below minus 20 dB. Minus 20 dB is this, that's minus 10, minus 20. So we can see that pretty much all the way it is below minus 20, and minus 20 would be pretty damn excellent. just here is where we touch -20. Anything below -30 is going to be pretty outstanding. So let's have a quick look. So we touch -20 really all the way over. Whoops, missed. Here at 2.944 gigahertz. Everywhere else we are a goodish amount below -20, and -23 would be kind of pretty much outstanding. There's -22.7. -22.8. And over here on the left hand side, below about 700, 800 gigahertz, we're actually below -30, which is really, really good. And even here, -24 at 927, not until we reach 1.3 gigahertz, really, that we -22, -23. So yeah, really good performance in terms of return loss. I will just change that so that we can see it in VSWR. And it's bouncing on the bottom there, so I'll auto arrange that just so we can see it more clearly. There we go. So these are this is 1 along the bottom line. 1.03, 1.06, 1.09, 1.12 and 1.15, which is kind of where we'd like to stay within. And you can kind of see that pretty much across the line until we reach nearly 3 gigahertz over here, it will match the worst point on the 2.994, something did I say? It will match the worst point on the other chart that we saw, the S11. We are pretty much below it. So it's actually the same pattern, it's just laid out differently, scaled differently, I should perhaps say. So yeah, so that's really good. Not unhappy with that at all. So this is going to be the transmission loss. So our theoretical best loss is 6 dB. Now there will be a bit of noise and a bit of error in here, but you know, nothing of any significance. And we can just kind of see the line is running right across the top of the screen here. This is 0 is the top of the screen, and then it's 10 dB per division. So I'm just going to, again, I think I will auto arrange that and see if we can get a better display. Yeah, that's better. So this line just here is the -6 dB line, and the second line down is the -7 dB. So we are pretty good across most of that line. And ideally I would measure the matching between the two outputs to see how different, how accurate the split is, if you like. But I'm not going to bother doing that. It requires a lot of grabbing data because I don't have the equipment to do it. I need a 4-port analyzer really, and I don't have one. And it means grabbing lots and lots of data and doing lots and lots of analysis. And this is just a quick, fun bit of work. So the results are in, and the dedicated resistor array was not surprisingly the best by a long, long way, giving better than 3 gigahertz excellent performance across the entire bandwidth. And then the discrete resistors weren't bad with, 310 megahertz excellent, 1.1 gigahertz acceptable performance, although that could probably be improved by choice of better resistors and making the board a bit smaller. The Bodge job with the surface mount was pretty good. Surprising, really. The commercial, well, we wait and see. I'm hoping the seller is going to send me a replacement for that. I've asked them to do so. We'll see if they do. If they do, I'll give them good feedback. If they don't, they can keep their bad feedback. The 3-hole, of course, was a bit dodgy. You know, okay, you could use it up to 130 megahertz, but I wouldn't want to really do so. So anyway, I hope you enjoyed that. It was just a bit of fun really, and maybe for a change actually seeing some of the results from some of these builds. And I hope you enjoyed it. If you did, please thumbs up, and of course subscribe if you haven't already done so. Comments down below as usual. See you soon. Bye.